Okay, so back to resonance. It's really unfortunate we're not in school because I have so many cool toys could show you with resonance. One of the things I will post, though, is a link to the Tacoma Narrows Bridge collapse. And I don't know if you've heard of it or seen it or not. It happened in the 1940s. Tacoma is in Washington State, and the Narrows is like a long inlet of water, kind of like the Bay of Fundy inlet, but skinnier. And so this bridge was over the inlet, and the bridge would be like the Westmoreland Street Bridge. But what they didn't realize when they were building it was that they built it so in such a way that its natural frequency of vibration was exactly the same as the frequency of the wind that often came down through this inlet. And so it didn't take very long. It took them, I forget how long to build it. It opened in July, and it wasn't very long after it opened that they began to notice that in the wind, the bridge would begin to move up and down like this. And they nicknamed the bridge Galloping Gertie. And people often went out with their video cameras because it would do this for a while. On this one particular day, though, it just kept going, and the amplitudes, and in the video, it looks like it's made of rubber, but it's actually concrete, and it's going up and down like this, and you can see like there's a car on it that can't get off. A scientist drove out to check it, and then he ended up having to walk back. And it eventually collapses. But it's because of this resonance. The wind was feeding energy in at exactly the right frequency. And when that happens, it doesn't just make a normal wave. The wave, amplitudes of the waves increase dramatically. They go out of control. And that's what happened to Tacoma Bridge. Another example happens in a microwave oven. Microwaves are on the electromagnetic spectrum, and we're going to talk about them in about 2 days' time. They actually have less energy than visible light. When we look at the electromagnetic spectrum, visible is here, X-rays are over here, and microwaves are down here. This is visible. So they actually have less energy than visible light. But when I get up in the morning and I beat my eggs together to make scrambled eggs and I put them under the light in my kitchen, they do not cook at all. But when I put them in the microwave, they cook in like 60 seconds. They're perfect and ready to go. So how come microwaves, which are waves that have less energy than visible light, can cook things so quickly? The answer is resonance. Microwaves have the same natural frequency of vibration as water molecules. And so what happens is whatever you put in the microwave has to have some moisture in it. And so when the microwaves hit it, those little molecules of moisture begin to vibrate bigger and bigger and bigger amplitudes. And remember, amplitude is energy. And so as they're vibrating with bigger and bigger and bigger amplitudes, that's more and more and more energy. And so it super quick cooks the food. And that's why some foods like those pizza pockets and stuff, when you cut into them, they're like scalded hot and you can give yourself third-degree burns because they're so hot due to the resonance. It's also why you should never put anything in there that doesn't have water in it, and why you should always stab a potato in a hot dog, because if you don't, then the water is now vibrating out of control and it can't get out. And so it explodes everywhere. Okay? In the lab, we have something that are called tuning forks. And again, those of you who are musicians, maybe you've heard of them or seen them. But a tuning fork has two prongs. This is its handle. These are its prongs. And then you hit it on something rubber. And when you do, it makes a sound. And we have tuning forks like that are 256 hertz and 512 hertz. And actually, after you hit them and you hold them up, you can see them vibrate. Like it's almost like your eyes are blurry, like they're going back and forth, well, like 512 times. So you'll come across these in questions in this unit. But I also have two tuning forks that are attached to two boxes, and the boxes are just opened boxes. And if you place them so that they're facing each other, and I hit one tuning fork, you'll hear it vibrate. But then if I put my finger on it, you'll still hear the sound because this one will have started. So one is forcing the other to begin. Another good example of resonance is if you've ever put water in your glass and then run your finger around the top of the glass to make it sing, you're making the air molecules in that glass resonate. Here's another one. It's a singing bowl. Now, let's see if I can do this. Sorry, if I just, my iPad is almost in the way. And so if I go at the right frequency, I can make the bowl resonate. Okay? All right, so all examples of resonance. And oh, another one. And that one is, have you ever seen those tubes? You used to be able to get them at the dollar store and you could see them all the time in the physics prep room by my classroom. It's an open tube and it's like plastic and it has like all these lines in it, and you hold one end and you swing it around your head and it makes all these wonderful noises. It's called an open-end tube. It's opened at both ends, and what's resonating are the air molecules inside of it. Okay? And then there's also a lab that we would have done if we were in school. And you take a graduated cylinder and you put water in it, and then you take a glass tube and you put the glass tube inside the graduated cylinder, holding it, of course. It's actually fairly long. And then you take one of those tuning forks I was talking about and you hit it and you hold it over the glass tube. And then you raise the tube up and down with the tuning fork above it, making it sound. And as you raise it up, you'll come to a spot where you'll hear what you just heard with the bowl. The sound will get louder and louder and louder. And what you've done is you've found the perfect length of tube out of the water that will create a standing wave at that spot, at that length in the tube. And when it creates a standing wave, it will begin to resonate. Okay? So this is considered a closed tube. It's a closed tube because the end in the water is closed. The end out of the water is open, but you can't have both ends closed because you have to be able to get the sound in. And all the water is doing is allowing you to change the length of the air column. This one is an open-end tube, opened at both ends, and we can't change the length of this air column. It's set, but we can change the speed with which we swing it over our head. And if we change the speed, then we'll get different resonating frequencies. We'll hear higher and higher and higher frequencies if you can go faster and faster and faster. Okay? So with that, we're going to move to one particular type of resonance, which are resonating tubes. The two types I was just actually telling you about. Okay? And so what happens in a resonating tube then is you're creating a standing wave in the tube. And in order for a standing wave to occur in a tube, at the open end, there has to be a node. And so if both ends are opened, you could have a standing wave that would look like this, or it could be a full wavelength, right? Like that. And remember the dotted side, remember a standing wave, it oscillates back and forth. So these would be for a tube that's opened at both ends. Has to have a node at the open end. For a closed tube, like the one with the water over there, still has to have a node at the open end, but at the closed end, it will be an antinode. It'll be a point of maximum displacement. Okay, and so we're going to look at open and closed tubes now and figure out how to solve for the frequencies in them. And I guess will probably be next video because I think we're out of time.